So good evening, everybody. And we are starting our third lecture. And the speaker is Tejas Kulkarni. I'm sorry if I'm not correctly.
Perfect. Yeah, that's good.
And actually, it is interesting because at our first day, we have a lecture of Alexei Dosovitsky, who have talked about wisdom competition and their model which win the deathmatch tournament at the wisdom competition last year. And he described his model about predicting the future values of the most important variables in the game. And their algorithm was based on this prediction. And today, Tejas, he was PhD student under supervision of Josh Tenenbaum at MIT. And as I understand, you have done work on predicting physical behavior of physical objects, yes?
Yeah, some of it, yeah.
Yeah, and today we have a talk which will be like a continuation of the talk of Alexei Dosovitsky about using prediction for planning and for playing in games. So let's start.
Yeah, okay. Thanks a lot for the invitation. And today what I'm going to talk about, I think, yeah, it's kind of in the spirit of what Alexei has talked about. And the main focus is going to be about predictions of the future. That's what the problem of reinforcement learning formula is. But it's going to be about predictions of not just values, which is what typically how people think about it, but predictions of your representations or of your features, and then tying it with rewards to get an estimate of the value. And we'll go into detail of what all of this really means. I spent some time at MIT, so a part of this work was the end of my term at MIT, and then also some of this work is something that a lot of folks here at DeepMind are quite interested in. So I'm going to talk about most of the work that I'm going to talk about is my work and some recent papers that actually end up using successor representations. So value functions. So I'm sure a lot of you by now have encountered these value functions, and feel free to interrupt anytime during the talk. I think it'd be nice to have a discussion back and forth. The main idea of state or state action value functions is that they are much more expressive, right, than the reward function. They express the discounted expected future rewards for any particular goal. So if we take state action values, which is what typically people will use for doing Q-learning, which is also in deep Q-learning, is you have some Q of pi, and you want to estimate for a given goal, you want to estimate the expected future features. So equation one, can you guys see all the mouse pointer by any chance? If I move it around. Yes. Okay. So this Q of pi essentially, typically you can write it down as the expectation of the sum of discounted reward. So R is immediate reward for each of the states, and this is your discounting factor. And so you start at some state as zero, A0, and then you sum your expected discounted rewards, right? You can, if you stare at this equation for some time, you'll notice a few things, right? You'll notice that basically your Q value function is essentially state dependent and action dependent, obviously. But it's also a sum of all the states that you're going to visit into the future, right? And the number of times you visit those states multiplied by the reward you get in all those states. That's basically what a value function or state action value function expresses, right? So we can rewrite equation one, which is what a lot of you must be familiar with equation two. And equation two is basically just saying that if you want to find out the state action value at S and A, sum or all of the states that you're going to visit from there. So that's S dash. The number of times you're going to visit them. So the M is basically a successor representation. That's what That's what we're going to call it. And M essentially denotes the number of times you visit that state, maybe discounted times that you visit that state, times your reward R. So equation 1 and 2 are basically expressing the same thing. And then we'll get into the details of when this is true and when this is not true. But most of the talk is going to be surrounded around equation 2, right? So we're going to we have broken down the state action value, disentangle the quantity Q into M and R, where now M is your expected state visitations under the current policy, and R is your immediate reward. So this is R is a supervised learning task, right? And M is essentially your reinforcement learning problem. And let's look at how M looks like. So if M denotes the expected state counts under the given policy, then it's simply essentially there's no function approximator here. So in the tabular case, it's simply going to be the number of times, so the indicator function of reaching S dash from S if I take an action A, and you just sum that, right? And this is obviously intractable with continuous states representation, and we can relax this. But conceptually, that's what M denotes. And if you notice, originally equation 1, you can solve that with TD learning, obviously, but there's only one TD learning problem, right? It's the expected rewards. But now in here, we essentially are now solving many different TD learning problems if your state dimensionality is more than 1, right? So essentially, it's the same TD learning problem, but the dimensionality of how many TD learning problems you're doing has just grown linearly with the feature space or your state space. And this idea was actually first motivated by Peter Diane in '93. So a lot of you might want to check that paper. It's a very nice paper. It's a neuroscience paper. And the original motivation actually came from studying rats that were placed in mazes, and they were trying to basically do navigation tasks. And one of the things that people noticed is in the rat brain, and even in a lot of other animal brain, especially in the hippocampus, there are cells or neurons that essentially encapsulate positions of where the rat is. And what people found out is that if actually it's not just the position, but each of these place cells actually not just capture the current position, but it captures the expected future positions that the rat is going to visit. So that led people to actually formalizing this idea, where if the rat was solving some policy or was trying to estimate a value function, then M would capture this expected state visitation, or in the rat terminology, this would capture the receptive field of where the rat is going to go next under some policy. And then the reward function is basically something where the rat might be going towards, food or whatever else it is rewarded with or punished with. So this is the original motivation of the idea. So now you can very quickly notice that equation 3 is obviously, this is intractable, right? So if you're doing deep learning, or if you're trying to learn these representations, then you really cannot do this indicator function, right? And you're not also going to be able to generalize as well. So one of the key things that you can do is obviously you can do approximate state counts. So now you can basically ask the question is, can I solve equation 3, but approximate the state counts? And that's what we're going to do next. So again, we're going to rewrite these equations. But one of the key assumptions now when you do successor representations is the following. The underlying assumption is the rewards are linear functions of your features. So if I have R of ST, actually, then you should be able to express the reward, the scale reward, not the value, the reward for this current state to be some function phi, and this could be a deep neural network, times W, which is just a vector of weights that you learn. But this actually is not a very limiting assumption, because right now I've indexed it as T, but you can imagine S of T, instead of just the current time index, you can have a recurrent neural network, right? So you can basically have a history of states, and then your features will be concatenation of all of your history, let's say a small portion of it, and then the assumption is still the same. You can take the history, you can get the features at that point, and then you can regress the reward from that point. If you make this commitment, and if you're fine with making this commitment, then you get out a really nice result, which is if you look at equation 4, which is typically how you write down the Q-value functions, you write them down as these expectations of rewards, as you have seen. Let's just kind of unroll that a little bit. So equation 5 is just rewriting equation 4, but with a few steps unrolled. So R of S0 plus gamma R of 1 plus dot dot dot, right? So now we can take each of these R of STs and substitute them with this linearity assumption. So each R is equal to phi at that time dot product with W. So we're just rewriting that for each of the terms from 5 to 6. Right? Now, if you notice in equation 6, there's something nice. Now you can, the features are different for different time points because observations are different. But the reward vector is essentially the same. So now you can pull out the reward vector W out from this expectation. So now you're left with equation 7, which now you have this expected features, right? Dot product with W. And M is what basically people call as successor representations. And there are various ways of interpreting this, right? But now essentially what we have done is we have disentangled the Q function into M and W. And M, you can think of M as a policy-dependent partial model, right? So it's a model-free way to estimate a model of the world, but it's policy-dependent. If you have just one policy, then it's policy-dependent. There are ways of having it be kind of dependent on multiple policies, but in the way this is written down in the most basic form is M is a partial model, and W is what represents your goal, right? So let's. Are there any questions? Because this is probably the most important thing that I want to communicate from the talk, and then there are a lot of ideas that follow through from these assumptions. But I just want to make sure that everyone understands what the key assumptions are and what you get out of if you make these key assumptions. Are there any questions?
So anybody has question?
Just to make sure.
Okay. Yeah.
To make sure that I understand and maybe others too, is M a learnable function? That is, it is a representation of a slice of future history that we'll learn to estimate pieces of history from the future.
That's right. So think of basically M is essentially it is learnable in the sense that you are now solving k different RL problems, right? So now you, instead of saying from a given state S, what is the expected scalar reward, cumulative reward I'm going to get in the future? Instead, now you're asking k different RL questions inside of M, where for each feature you're asking, under this policy, what is my future going to look like? What is this neuron going to predict? So in principle, it is a learnable function, and then empirically we also find that it is learnable indeed. But I mean, it's an open question. You know, when does learning slow down? When does it speed up? And that's an empirical question as well as a theoretical question. As under what conditions is M learning M is basically more harmful than learning just the expected rewards. And I think maybe the short answer to that is once we start thinking about multiple policies, right? So not just pi, but we think about pi 1, pi 2, a set of pi's, and then a set of successor features. Then things start getting really interesting. Then it might be worth learning M, because then for each state, you might actually have expected features under the policy, minus information about the goal, which is nice, right? Because the information of goal is not meshed up into M, so it's quite nicely separated. So it might make more sense when we're actually learning many different pies. But even when we're learning a single Q function or a single goal, learning W is actually quite easy, right? I mean, in the case of navigation, imagine that you have a few waypoints that you want to visit. Learning W is going to be quite quick with supervised learning. So you might be able to get your goal inference quite quickly, but then learning M might be much slower as opposed to learning the whole two-function integral learning.
Any more questions? We have. We would like to ask you. Can you do you have a, because we have a little bit poor sound on our side.
Ah.
I don't know if do you have external mic or just use one in your notebook.
I don't have an external mic, but is this better?
Maybe you just talk closer to your laptop. Maybe, I don't know. Is it
okay? Is this slightly better?
Yeah, it seems to.
Okay. I now also talk loudly. Unfortunately, I don't have a mic, an external mic.
No.
Okay, so so moving on. So I mean, why do this? I think we talked a lot about why do this, but a few more reasons, right? One of the main reasons is this distribution of goals is highly non-stationary. Basically, imagine the case of robots, right? Imagine a robot arm that wants to reach a moving object, or where the space of goals is changing quite quickly. The question is, how do we build deep reinforcement learning systems that more flexibly and principally handle distribution of goals that are non-stationary? So that's question number one, which leads you to think about these kind of things. Then the second question is, if we want to build models, partial models of the world that are policy dependent, and many partial models of the world under many questions or goals, then is there a model-free method to learn these models? And the successor representation is essentially a take on that, right? You're saying that let's build a partial model of the world with TD learning, and it might, so it doesn't really substitute a full model, right? Because in a full model, you actually can predict the next state from your current one. So if we go back to the equations, I just want to kind of draw attention to relation between a full model and a successor, a partial model, where M is essentially this quantity in 7. If my gamma was 0, right? So my discount factor was like really small, then I'm essentially predicting the next features that I'm going to see, right? Which is typically what you would do with a model, right? You'd look at the current state or features in this case, and then you'd predict the next features. But as gamma increases, you're essentially predicting a summary statistics of what your model is going to look like, or your states are going to look like in expectation. And that's basically the key link between a full model versus partial model, right? Obviously, the other thing is to decouple learning dynamics into fast and slow processes, right? So imagine a navigating agent. It should be able to quickly change its path as the goal space changes, right? Without relearning too much, but keeping around a lot of what it already knows, but only changing some parts of the network. And the most important one, and I think I would advise almost all the students to read this paper if you haven't, is in the transfer learning scenario. So Andre Barreto, David Silver, and a bunch of others at DeepMind, they actually have this very nice paper on successor features for transfer learning. And in that scenario, basically, instead of asking the question, what is my Q-value function, what is my successor function M under one policy, they're saying if I'm solving a new goal, so the new goal could be, you might have, imagine a maze, and your robot might have basically went to many different target locations. Or if you have a robot arm, and it might know how to pick up objects in many different target locations, right? So imagine those different target locations are different goals. ranging from pi1 to pi(n), and you've learned the successor features for them, right? So m pi1, m pi2, m pi(n), and now you're given a new goal that you've never solved before, and that's wn+1. So it's a location, let's say in the robot case, an object in a location where it's a new location, right? The question is, what is the best thing you can do? And it turns out that if you actually take the argmax of your m under all your previous policies, and dot product that with your new goal, then that's a reasonable Q value approximation to the problem. Under a few kind of considerations that are details, and you should look at Andre's paper for that. But this is I feel like if I want to communicate one thing from this talk, I want to communicate equation 9, that if you're solving k different tasks, learn k different successor functions, and then for the new kind of goal in that space, wn+1, use all of your previous successor functions. So keep them around. Instead of throwing them out, keep them modularly, and then just take an argmax max, and then get a new policy evaluation up. So now I think these are all the principles. So I think hopefully now I think everyone understands the assumptions and the basic principles behind what goes off in successor representations, right? And what's possible. And now I just want to show a few kind of experimental data points to know that this can be done. Like you can learn M, you can learn W, you can do these things from pixels. But by no means this is an optimal architecture. I think this was like the first shot that we took, and there's a lot more work to be done. So it's fairly fertile research grounds for people to kind of take these ideas and try to see how far you can push with that. So I'm just going to give you a few, just one kind of almost a pedagogical model architecture, just to illustrate some of the points, right, of how to do this. So you take in your states S, which is your observations S, which are your raw images. You pass them to convolution neural nets, and you get some feature phi. So ignore this branch for now. Ignore this because there was a reason why we had it, but ignore that for a second. Let's focus on two branches. So from phi, we're going to predict reward R, right? As we talked about, where W is essentially some vector, and we regress out the immediate reward. From phi, we're also going to read off. We're also going to predict the successor feature M, right, for each of the actions. Right. So if I have 10 actions, then I'm going to have 10 expected feature successor representations. Right. And then the way we can train this system, and I think the third thing, let me just say what this really is. This is just an autoencoder. So I basically the only reason to do this was to see where all losses could be injected, right? So feature phi could be trained from rewards. It could be trained from successor features potentially, but it also could be trained from some auxiliary losses, right? And I think you must have heard in other talks about people are now making use of auxiliary losses. And this is just one way of putting one more auxiliary loss, which is reconstruct the frame, right? So you might get some contrastive term through this, and you can stick in many different types of auxiliary losses potentially here, and that's a interesting kind of exploration to do with these kind of ideas. But the three loss functions, I guess in this case, one of the and two of them are strictly necessary, right? The first one that's strictly necessary is the loss function on the successor representation, and the loss function there is a Bellman update. And a lot of you must be familiar with this from Q-learning, where typically the Bellman update in Q-learning is your reward, but in this case we're going to have the feature. So now we're trying to predict features plus the discounted M of your next state minus some target network. So M past is like in DQN, if some of you might have implemented it. Basically for stability, we basically make use of a target network. and update it once every while, right? And this equation essentially is the loss function being propagated through here. The other necessary one is reward, right? So you want to back propagate the immediate reward from R all the way through these features. And then the third thing is you want to, in this case, it was an auxiliary loss. So in this case, it was autoencoder, but you could imagine different types of auxiliary loss functions in this case. But so that's the generic architecture. And if you do this, I'm just going to show you some illustrations and then and then show you an interesting kind of use case of why successor function. What can you buy from them if you do them? But the first test case is, can we just learn all of these things end to end, just a sanity test, right? On both the 2D maze and as well as some very simple 3D navigation wisdom. And this was done using deep Q learning with an experienced replay buffer. But the main agent architecture is I mean, I think I'm hoping that us and a lot more other people play with different architectures. And this by no means is the fastest way to train a navigation agent. Alexei told you about these actor-critic agents that are much faster. They're less sample efficient, but they're much faster because you have multiple threads and eligibility traces. This agent is very basic, so it's just meant to illustrate the point. And I just want to show you the videos first. So this is just, oops, I don't know why I can't run the video. Unfortunately, the video is not playing.
Maybe you should switch from the full screen mode for the presentation.
Let me just see. I mean, it's not super important, but you can see this web page, right? Okay. Anyways, I mean, I think a lot of you have seen these type of wisdom navigation tasks, right? So this is just, I mean, I think this is just GitHub. Unfortunately, the video I have is not playing. We can try again. But anyways, I think these are mazes where the agent has to go from point A to point B, maybe collect ammunition, so on and so forth, right? And you can train these agents, and they actually work reasonably well. 1 second. Let me go back. The most important thing that I want to focus on is how do these things actually adapt to fast changes and distal changes to rewards, right? So, like, imagine essentially you have to get to a goal location, but in the most simplest case, imagine if your agent's reward values or preferences change. So instead of it getting a +1 reward at the end, it gets +5, right? This is the simplest case of reward changes at the goal location. So typically, one of the issues with something like DQN is if DQN is in the dotted line. So these are the dotted lines. So what you're seeing here, this graph, is both the DSR and the DQN agent were trained on a maze task, right? So it's basically had to get from some point to some other point, right? So you train it. And then the simple test here was, what if the reward, there was a change in the reward function? Like, how fast can your Q values adapt to the change in the reward function, right? So after you train both of these agents, you put them into the maze again, but now you change the reward function. And what you'll note, and then you track their Q values. So on the x-axis is training step from 0, but when you start from 0, these are trained agents, right? On that goal. Y-axis is basically the Q value at the origin. So when you start, the spawn location is kept the same. And what we're measuring here is after convergence, or as you run the training loop, as you get more and more experiences, how fast does the Q-value function adapt to the change in your rewards, right? So kind of expectedly with DQN, because your rewards are mixed with your expected features, right? It takes a long time for DQN, right? I mean, because you just have to kind of relearn your you have to repropagate your Bellman updates. They have a high error now. You have to do some backtracking all the way back, and then that takes that's going to take a lot of samples, right? But if you take the successor agent, one nice thing by construction is that the reward is disentangled from your successor features. So if your reward changes, you can simply do supervised learning on that. When you hit the reward location, learn, and then your successor features, depending on how much they change, if they remain the same, then the value gets propagated instantaneously, right? So this is just a nice kind of pedagogical example of how you can do very quick Bellman updates if you separate the goal representation from your Q network or your value network. I hope this is clear. Sorry, was there a question or comment or?
Yes, we have one question.
Yes.
Could you step back for a slide with the architecture? I have this one with the three types of the loss.
Yes.
Am I understanding correctly that autoencoder loss is pushing our net to produce some meaningful explanation of the picture, which you try to from which you try to get the reward or some I mean the immediate reward and TD. So my question is, if you're changing the autoencoder loss to some other loss, is it still be working? It's not obvious to me.
Oh yeah, good question. So recently, this is not. Oops, there's a lot of echo. Okay, so that's a really good question. In some recent experiments, what we found that it actually works without autoencoder loss even, right? So let's say if you get rid of this loss, and if you backpropagate just from these two, right? In the version that we tried, actually this phi had a few fully connected layers, and then from there we just directly predicted the reward and the successor function. And in that case, you actually can have the system does work. I guess with the autoencoder, the hope here was in some cases, if your reconstruction loss might help you to do better reward predictions, or it might help you to learn better successor functions. But the jury is still out on that. It's not clear to me either. Like when is it required? In what capacity is it required? There are some recent experiments I've seen where people are trying to learn disentangled representations. So using some disentangled autoencoders, which can help you learn better value functions. So there's so it requires some more research to know when and how can auxiliary loss functions actually help do the reinforcement learning task. But it does work without this.
Thank you.
Yeah, I think in the original paper, I was not backpropagating from the successor branch. I was clipping the gradient of this guy up until here. But if you let it go all the way, and then also predict the reward, then you can basically train, even when you have sparse reward, maybe you can train this entire network just with these two losses. And that's actually internally at DeepMind, that's the kind of version that we're playing with now. It doesn't really, I'm not right now playing a lot with these autoencoder losses as much. There's one more interesting. There's one more really interesting thing that you get out if you do this, which is, one of the questions is, how do you do hierarchical reinforcement learning, right? How do you get temporally extended abstractions? And there are many ways of thinking about this problem. And I think if we take a bit of a bottom-up view, then you can start framing it this way, like learn SR. Let's say you learn an SR under some random policy. Not that this is the best thing to do, but I think it kind of illustrates the point. And what this means is, imagine a maze where you walk around on the maze randomly, or it could be under many different policies, right? So in this case, since there is no goal, I guess you're not getting any reward, right? You're just learning the autoencoder. So this is where the auxiliary loss for me was important, because if I'm doing latent learning where I don't have an explicit goal, then I'm not going to be able to learn really good features. And if I'm just learning expected features, well, what are the features dependent on if I'm not getting a reward? So that's why I was experimenting with autoencoder losses. It was for these bottom-up subgoal discovery like problems. Anyway, so you walk around a lot, you're doing this autoencoder for each frame, and you're also predicting the expected features. So now once you do this, for each state, right, each observation that you get, you will have a corresponding SR, right? So for S1, you might have MS1A, MSTAT, so on and so forth. Now you can take all of these successor representations and then essentially create an affinity matrix. And I'll go into the details of what the math looks like, but I just want to make the point pictorially first before I explain what the details are. But you have these successor representations for each of these points. You build a graph of some sort, and then you essentially try to find these normalized cuts in the graph. So what we are really looking after is let's say in the navigation problem, eventually what we should find in terms of good sub-goals are things like doorways, right? Because these things are states or observations or experiences which essentially connect two very big regions of experiences. So if I'm in this room and walking around in this room, I'll collect a bunch of experiences, and then I'll collect a bunch of experiences here, and here. But if I want to go from a set of experiences here to there, I have to pass through a bottleneck. And that bottleneck is basically what we're going to interpret here as a sub-goal. And if you do this, then you can essentially have these plausible sub-goals, which then you can feed it into a hierarchical agent, so it can learn the sub-policies or policies to reach from a given point of space from here or here, how to reach each of those sub-goals. So that in the future, you can do much better graph traversal, right? So it essentially, what we have done here is we have used the successor, the representation to give us basically the bottleneck states in the graph of your experiences. And more precisely, how this actually looks like is you collect SRs for each state under a random policy. Then you create an affinity matrix W given SRs under a radial basis function. I mean, it can be any kind of function that relates two different SRs, a metric function. So this basically just gives you a sense of, from two different points, if they're very close to one another in topology, then they will share the same expected futures, right? It's quite intuitive. Then this gives us a diagonal matrix, which we can construct, which is D from this affinity matrix. So this diagonal matrix, then if you take the largest, and these are details. I mean, I think you should just look at these papers that I have cited. But just for completion, if you take the second largest eigenvalue of the matrix, of this matrix, then that gives you an approximation of the normalized min cut. And that's essentially, and then the states that lie along the endpoints of that cut are plausible subgoal candidates. And these are the subgoal candidates that we talked about. So the end result is you essentially get these black things. These are specific experiences that are subgoals, or good waypoints, if you will, in the navigation sense. And for statistical robustness, you can randomly sample a subset of SRs and collect statistics of how many times a particular state lies along the cut. So this is basically just doing a bit of statistical kind of robustness. So you can take the original problem, select a few experiences, there could be millions of them, run the algorithm, get some subgoal candidates, select some other experiences, run the same algorithm, and then basically just try to find subgoals that persist across these different tests, right? And then you can actually have those as your subgoals. And if you do this, this is basically just a sanity test, or just an illustration in simple cases, where in the maze cases you might have a 2D maze of pixels, where the agent might just go around with walls, or a 3D maze that where it is the same thing, but it only sees partial images of the maze. So in this case, it's fully observable in the sense that you see the entire pixel space, right? But the agent does not see anything else. But in this case, it's partially observable. But if you run the algorithm, then you can start discovering these bottleneck states, which are near the doorways. This is starting to get at the question of, for at least for some types of problems where bottleneck states are semantically can be categorized as these min-cut problems, which are a lot of these navigation problems, maybe manipulation problems, locomotion problems. Then we can perhaps start learning more high-level kind of planning algorithms, but get these representations by learning these successor functions, right? So I just want to kind of leave you with this image of a good direction to explore of how to get kind of bottom-up subgoal candidates. There are a few caveats that I will mention. The first thing is SR is policy dependent, which means that your successor function it's not a full model, it's a partial model. But I think Andre Barreto's paper kind of pushes us of ways of combining multiple SRs via the max operators, and I talked about this a little bit, and I think you'll see more of this kind of stuff coming out. The reward functions needs to be linear with respect to features. I guess in the deep learning land, this is not this is in principle possible with recurrent neural nets. Although I mean, this is a big assumption to make, right? Because in cases where rewards cannot be expressed simply as linear features, as linear functions of your features, that is problematic. Perhaps one way to kind of think about this would be hierarchical successor functions, where some high-level policy might spit out low-level kind of reward functions, intrinsic reward functions, where piecewise these intrinsic reward functions might be linear functions of your features, and that might be a way to approach this or relax this limitation. The final one, which is a very important one, is learning SRs for a single policy does require the k different or the dimensionality of a feature space, different simultaneous RL problems, right? And this can be good and bad. I mean, I think depends on what you want to do with this, but you do get more signal. But on the other hand, if you just care about solving a particular goal, then this might or might not be a good idea. It really depends on the problem. The potential is obviously, I think we talked about a bunch of this, but I just want to close off by saying things like pre-trained visual features really from the current RL tasks, by having many auxiliary functions, adaptive preferences, where we might have a robot that might basically say that, oh, I just want to now consume only 50% of my energy. So how should it? Maybe it should, instead of running now, it should walk. Or you might have different drives for different agents. So then the question is, if these preferences are changing quickly, then your values should change quickly, right? So agents with preferences is something that we might be able to start kind of thinking about with these end-to-end DeepHack like systems. I guess transfer learning in scenarios where the goal is changing quite quickly is something that Andre's paper talks about, and that needs a lot more work. And I would encourage people to kind of, if anyone wants PhD projects, I think there's a lot to do in terms of thinking about multiple successor functions and doing transfer learning in different scenarios. And finally, I think the more ambitious one, and where this is quite hard, but you can start thinking about ways of creating these bottleneck states by decomposing the successor representation recursively. And that might be ways of incorporating these in hierarchical reinforcement learning systems. Anyways, if there are any questions, I'm happy to answer. But you can also kind of play with the code, look at the paper, try some of these ideas. There's a lot to explore here.
Okay, thank you for the great talk. And questions?
Okay. Hello.
Yeah.
You mentioned training the network without giving it rewards. So
yes.
Okay. So did you try first training it without reward and then giving it reward? Does it perform better than just giving it reward from the beginning?
So it depends on what you want to do, right? So in this case, if you look at in the subgoal discovery case, you might so one thing that you might actually do, which might be a good idea, is before you actually know what reward you want to solve in a maze, let it run around a lot, right? Maybe let it run around so that it can go across, collect many experiences. Maybe get these subgoal candidates. And then when you are actually exploring for a particular reward, use these policies to go towards these subgoal candidates in your exploration policy. So when you're typically starting an agent for solving, let's say, getting to a target location, you would maybe have an entropy cost or epsilon greedy, right, as an exploration strategy. But what I'm kind of referring here is maybe you can do a lot better than epsilon greedy in some specific cases like these, right, where you run you do some latent forms of learning, you get these sub goals, you train in an off policy way, getting from some part of the state space to these sub goals, and then when you're actually running your agent on a particular goal with particular reward function, then use this in your exploration.
Okay, thank you. Any other questions? I have one more question for you. Yesterday we have a talk of doing a Prekap, and she discussed her work on options on temporal abstraction and reinforcement learning.
Yes.
So can you talk a bit how these successor representations are related to the options theory? Because all this stuff with locating goals and learning different policies for different subgoals, it seems to be conceptually very close to the options framework.
Yes. So actually, if you think of, let me actually pull up a figure if I have it somewhere here. Can you see this? Yeah.
Yes.
So you can imagine essentially a hierarchical agent, right? So you can imagine that on the top comes your task plus noise, and then there is some Q2 agent that essentially outputs a reward function W, I think this might be a very difficult figure to parse, unfortunately. But this agent essentially may actually pass an intrinsic reward function. So you can think about it as an option, right? And this agent then can actually output a more in even more abstract reward function. And finally, you have this agent Q0 that is taking the real actions. So if you look at the hierarchy of agents in an HRL setting, where each of these, you can interpret each of these levels as an options model, right? Then abstractly, the successor features are essentially can be expectations over your options or your subgoals, right? So you can learn an expected model of not just the features, but you could also learn an expected future model of your options, and that gets to the idea of things where you can essentially then do the same things, where now instead of your Q values being over atomic actions AFT, the Q values can be over your intrinsic reward functions. But they might take into account the expectations of your intrinsic reward functions, or the kinds of option futures that you're going to see, independent of the actual intrinsic reward function or the scalar values of them. So that's I would say that's the connection between these two things. They're quite complementary, because successor function essentially is almost a learning process. It's a specific type of prediction commitment, and which can be used within an options framework. It's not something that I think I have tried, or I haven't seen anyone trying that, and I think that's a good place to explore. But I think the links can certainly be made there.
Okay, thank you. Any more questions? No. So thank you for the talk.
Thank you. Thanks a lot, and feel free to email me if anyone has any questions and thoughts or concerns, whatever.
Yeah, thank you.
Yeah, thank you. Bye bye.